Hey everyone, welcome to today's Explainer. Everywhere you look in AI tooling lately, there's this pervasive, almost foundational myth taking root. It's the idea that natural language, just plain conversational English, is going to completely take over and become the ultimate interface for absolutely everything. But is that actually true? Well, today, we're going to completely dismantle that idea. We're going to look at the hard science of why your next programming language probably won't just be English.
Okay, let's dive into this. Here is our roadmap for today. We'll start by unpacking the natural language myth, explore the specificity crossover theorem, examine real-world modality clashes, climb the ladder of specification, and finally, look at building hybrid AI systems. All of this is based on a highly anticipated position paper slated for ICML 2026 by researchers Wagner, Rosenzweig, and Abend.
All right, starting with Section 1, the natural language myth. Now, to really understand where these researchers are coming from, we have to acknowledge the massive, undeniable shift in developer tools recently driven by large language models. The prevailing industry hype essentially asserts that natural language could entirely replace formal languages, right down to the actual programming languages we use in software design. I mean, you hear it everywhere, right? Well, this is the exact claim that the researchers directly challenge in their paper.
Which leads us to a pretty pivotal question. Is natural language actually fundamentally built for this level of precise specification? When we strip away all the hype, what does the linguistic science actually say?
That brings us to Section 2, the specificity crossover theorem.
The central theory of this research sits right at the fascinating intersection of computation and language. What's really interesting here is how it frames communication purely mathematically. The authors define task specificity as the information-theoretic reduction of uncertainty in an output space. Think about it like a giant puzzle. When you give requirements to a system, whether it's for generating an image or synthesizing code, your ultimate goal is simply to reduce the uncertainty of what comes out the other end.
But here's the catch. The tools we use for this are vastly different. Natural language is actually optimized for underspecification. It thrives on open-endedness. It's exactly why you can order a coffee without specifying the exact water temperature and extraction pressure. It naturally omits irrelevant details and relies on pragmatic inference. Formal language, however, is designed to strictly and mercilessly eliminate all ambiguity.
And this brings us to the core mathematical contribution of the paper, the crossover threshold. The researchers prove there is a literal mathematical point, a threshold, with the token cost and the human cognitive overhead of forcing exact rigid constraints into conversational English increases non-linearly. Beyond this threshold, conversational English just fails. Trying to type out exact memory allocations or specific type signatures in paragraphs of prose actually becomes vastly more expensive than just writing the code. Direct formal specification scales linearly, forcing it into English explodes in complexity.
Moving on to Section 3, real-world modality clashes.
Let's step out of the theoretical math for a second and see how this crossover threshold plays out in practice across different types of media generation. And this brilliantly illustrates exactly where English works and where it hits a wall. Natural language has distinct strengths. It's amazing for drafting boilerplate code, describing high-level architecture, or setting the stylistic mood and genre of a song or an image. But the moment you cross that specificity threshold, English fails. You absolutely need formal parameters for exact memory, safety, and concurrency primitives in code, specific seed controls and aspect ratios for an image, or exact sample rates and channel configurations in audio. Those formal requirements are simply non-negotiable.
All right, Section 4, the ladder of specification.
To solve this clash, the researchers propose viewing these languages as existing on what they call a ladder of specification, fulfilling complementary roles. If you ignore this boundary and force everything into prose, you're going to hit a massive wall of latency. We've all been there, right? You end up wasting 40 minutes trying to get an AI to write a perfect regex just because it couldn't infer your exact intent, and your context windows completely explode from wasting tokens on verbose English constraints. The paper even points out that benchmarking AI code generation solely on natural language prompts completely obscures these underlying inefficiencies.
So we explicitly map out this ladder. On one side, natural language handles the boundary conditions beautifully. It's absolutely perfect for requirements gathering, writing documentation, and debating architectural trade-offs. On the flip side, formal languages step in for the strict constraints, your type definitions, your configuration files, and domain-specific languages. They are really just two halves of the same whole.
And finally, Section 5, building hybrid AI systems.
So what does this all mean for us?
What actionable steps should developers and product managers take right now to adapt their toolchains to this reality? Let's move to and see how this builds into 4 specific strategies from the authors for creating hybrid systems that actually outperform pure natural language interfaces.
First up is layered prompting. The idea here is to use natural language to convey your general intent, like fetch user profile with fallback cache, but then pair that directly with structured parameters like a JSON object for the precise requirements. By passing a timeout of 200 milliseconds and max retries of 3 as a formal constraint alongside your prompt, you instantly minimize token waste and enforce type safety. It is incredibly elegant and it prevents so many hallucinations. The remaining 3 strategies really focus on advanced system integration. Second, you need formal validation loops. If the AI outputs natural language descriptions of code, your system needs to parse those into executable formal representations before doing anything else. Third is context window management. Pin those formal dependencies down so you weren't eating up your active context size. That dramatically lowers inference costs. And finally, modality switching. AI toolchains must have interfaces that let users seamlessly toggle between descriptive English modes and declarative formal syntax modes, aligning their cognitive load perfectly with the task's specificity. So the crucial point is this. Treat the model as a translator between intent and formal execution, not as a direct substitute for a compiler or a designer. True efficiency and real cost savings don't come from trying to kill off formal languages. They come from respecting that crossover threshold we talked about earlier.
I want to leave you with this final, provocative thought to consider. If natural language is just the starting point, just the top of the ladder, how will you redesign your own workflow to truly embrace the strict constraints of formal execution? I highly recommend checking out the full ICML 2026 position paper on Archive for all the mathematical proofs and start thinking about how you can build better hybrid systems today. Thanks for joining me on this explainer. Keep learning, and I'll catch you next time.